So as we've been studying triangles, we are going to look at some different segments that will be special, have special names, special properties, and points of intersection. So the very first thing we need to talk about is this terminology, points of concurrency. So this is just a place where three or more lines intersect at one place. So it's really easy to get two lines to intersect, right? As long as they're not parallel, you always get two lines to intersect. But when you get three lines to intersect and they intersect at one point, that's that point of concurrency where they are all intersecting. Now, we get these different names. This first one that we're going to take a look at is what's called the circumcenter. So that's a point of concurrency where the three perpendicular bisectors of a triangle are going to meet. So on the bottom, I've given you three different triangles. This first one we can take a look at. I'm going to call this an acute triangle, since all of the angles are less than 90 degrees. I'm going to call the second one a right triangle, because again, it has one right angle. And I'm going to call this last triangle an obtuse triangle, because it has one angle that is obtuse. In general, all triangles have two acute angles. Maybe make a little note to yourself. All triangles have two acute angles. It's that third angle that determines the name. So in this case, two acute angles, I take a look at the third is also acute. Two acute angles, I take a look at the third is right. Two acute angles, I take a look at the third is obtuse. So that's how we name these. Okay, I'm going to pull up a calculator file, and you're going to notice the triangles on the calculator are going to look like these. And what I want you to do is observe where the intersection happens. And what I want you to do is maybe sketch an idea of where that intersection, that point of concurrency, in this case the circumcenter, actually falls on the triangles. So when we take a look at this first one, okay, your point of concurrency is going to be over here. So right where all three of these lines meet, that's your point of concurrency. Now this is an acute triangle. When I take your triangle and I move it, so now it looks more like a right triangle. Take a look at where that point falls. Looks like it's falling right on the side, in particular the hypotenuse of the triangle. When I make it an obtuse triangle, notice it falls on the outside of the triangle. When it's an acute triangle, notice that point is on the inside. So the big thing here is notice how it can change. It could also be on the outside, it depends. Maybe it's going to be on the triangle, it could fall on the triangle when we have a right triangle. And then once I have an obtuse triangle, I see it's definitely going to fall on the outside. And this will work for any point I chose. So if I make a different point move, again, I can see those points moving, and I can see where that point of intersection falls. Okay, so now something to keep in mind, any point on the perpendicular bisector of a segment is equidistant. It's equidistant from the endpoints of the segment. So if I were to take a look back at our picture here, any point on the perpendicular bisector, so anything along this line, is going to be equally distant from the endpoints of the triangle, endpoints of the segment. And if we go back, we can take the converse. We can switch it around, switch the order, saying any point equidistant from the endpoints of the segment lies on the perpendicular bisector. Okay, so that's one point. Next point of intersection that we're going to take a look at, next point of concurrency, is called the incenter. The point of concurrency of the three angle bisectors. So what that's saying here is for each of the triangles again listed below, I'm going to construct an angle bisector, one at each vertex, giving us 3. And then we're going to take a look at that point where they all meet. That again, that's going to be called that point of concurrency. And for angle bisectors, that's the incenter. So when we take a look at this, I can see right now to begin with an acute triangle, that point of intersection, the incenter, is inside the triangle. If I move this triangle around, maybe I make it a right triangle, maybe I make it an obtuse triangle. Notice what's going on. No matter how I move this triangle, that point of concurrency, it's always inside the shape. It's never leaving. And it's never going to be on. So this is different from the perpendicular bisectors, that circumcenter, and the fact that this point of concurrency is always inside. So every single one of these triangles down here, we are going to say it is always inside. The incenter is inside the triangle always. Okay. Now we get another segment. And this is a median. A median is a segment connecting a vertex to the midpoint of the opposite side. Okay. When we connect and draw 3 medians, again, one at each vertex, the point of concurrency of the medians is called the centroid. This kind of has some special properties, some algebraic properties that will go with us. Not only is this called the centroid, but sometimes this point is referred to as the center of gravity. Okay, so if we found that centroid, we found that point where all the medians intersected, that would be the center of gravity of the triangle, and we could try and move the triangle around, that would be the balance point. Okay, so again, I'm going to pull up some pictures. We're going to take a look at what happens when we move the medians around. So again, for the medians, the segments are going from a vertex to the opposite side at its midpoint, and all of these, from a vertex to the opposite side at its midpoint. This being an acute triangle, again, we're starting off that intersection point where all 3 of those medians intersect. That is going to be our centroid, is inside the triangle. If I were to move the triangle around, try and force it maybe into a right triangle, maybe an obtuse triangle, I've never seen that point leave the triangle. It's permanently fixed inside the triangle. Doesn't matter how it's stretched, shrunk, that point is always on the inside. So again, maybe a little note that you want to draw some pictures to remind you of it, but this is always on the inside. Okay, now with this centroid, we get some algebraic properties. It says the centroid divides the medians into a 2-to-1 ratio. The section of the median nearest the vertex is twice as long as the section near the midpoint. So if we're looking at the picture, it says we're going to label the lengths of segments DF, GF, and EF as X, Y, and Z respectively, just meaning in that order. So DF, we're going to label X, GF, I'm going to label Y, and then EF, we're going to label as Z. Now, I have to label the other sections. I have to label CF. Well, because it's in a 2-to-1 ratio, if DF is 1X, that means CF is 2X. Okay. Same thing with AF. So I know GF is 1Y, that means AF has to be 2Y. And same thing with BF. Since I know EF is 1Z, that means BF has to be 2Z. So there's that 1-to-2 ratio. Okay, now connecting some values with it, we're going to take a look at this picture down here, but now this time have some numbers. So it says in the figure to the right, DF this time now has a value of 4. BF we know has a value of 16, and AG, the whole segment AG, is 30. So we could just kind of fill in this picture and then fill in the blanks to the right. Label what you know. So in that 2-to-1 ratio, we said if DF was X, FC was 2X. So this section here, FC, has to be twice as big as 4, in other words, 8. Taking a look at EF, and I know that BF is 16, I know EF was only one part of that 16. So EF was Y, FB was 2Y, so that's twice as big, meaning EF has to only be 8, or half as big. Now when we look at AG, if we take a look back up at top, AG was made up of both 2Y and 1Y. They're telling us AG over here is now 30. So I should be able to say, so 30 is equal to 2Y plus Y. In other words, 30 is equal to 3Y, which would tell me then Y has to equal 10. So that means FG must be 10, and AF must be 20. So let's fill in our blanks over here. We've just labeled our picture. So FC we know is 8. DC, so that's the entire segment, adding up the 4 plus the 8, so that's going to get us a total of 12. AF we found to be 20. BE, so again, adding up our 16 plus 8, so that's going to get us a total of 24. FG we saw was 10. And lastly, EF we saw was 8. And then the last segment that we have, so we have 4 special segments here, is an altitude. An altitude has an endpoint at a vertex and the other line that contains the side opposite that, so its segment's perpendicular. So in other words, it's a perpendicular line. It starts at a vertex, goes to the opposite side, and it's perpendicular. It does not have to be at a midpoint, it just has to be perpendicular. So the 3 points of concurrency, the point of concurrency of the 3 altitudes forms what's called the orthocenter. A lot of times we hear the word altitude also connected with the height of a triangle. So anytime you're trying to measure the height, you're looking for the altitude, or maybe they've given you the altitude, that's going to be the height that you want. So we're going to take a look at our last picture. These are the altitudes. So they're starting at a vertex, it goes to the opposite side. Notice not at a midpoint, it just has to be perpendicular. So it starts at a vertex, goes to the opposite side, it's perpendicular. And again, notice where that is located right now. So that's your orthocenter in the center of the triangle. If I move it around, so now I've got a right triangle, and notice where that orthocenter is. It's actually right where the right angle would be. Now I move it on the outside, and while the 3 lines aren't intersecting, I could extend those lines, and I could actually show you, yeah, that's always going to intersect, but it's going to be on the outside of the triangle. So if I wanted to extend this line down, and extend this line down, extend this line over, I could see that that would intersect outside. So we have on, we have outside, we have inside, and if I move it around, notice what's going to happen. It doesn't really matter. It could be on, could be outside, inside, and that works for any vertex. So it doesn't matter the vertex that we have chosen. This is a segment that will change location depending on the shape. So it could be outside, it could be on, it could be inside. So these are 4 segments with 4 points of concurrency. We have to memorize their names, and we have to memorize where they intersect. So maybe flashcards would be helpful to get this committed to memory. Hope this helped.